Okay, so we're going to talk about properties of tangents today. So first of all, we're going to quick review what a tangent is from our circle vocabulary. A tangent line intersects the circle at exactly one point. Okay, it's always outside that circle too. That's what you're looking for. So in the diagram below, to the right, line L is tangent to circle C at point T. So here's line L. It's tangent because it hits this circle exactly once at T. Okay? That's outside that circle. So determine which of the following are tangent lines. Write yes or no. All right, so here I see a line. It's outside my circle. It hits one time, so that's a yes. The second one, here's a line. I see parts of it outside and part of it inside, so that's already looking like a no to me. And I see that it intersects twice, so that's a big no. The next one, a little tricky. It looks like it only hits once. But it's not outside the circle, okay? And you have a line going through the circle. So this is a no. That's actually just a radius, right? This one hits once, that's looking good, outside the circle, so that's a yes. And the last one, inside the circle, so that's not good, and it hits twice, so that's a no. Okay, so make sure you have a tangent line when we're working on the properties that we're going to learn today. All right, our first theorem for today. If a line is tangent to a circle, then it is perpendicular to the radius at the point of tangency. So as a reminder, the word perpendicular means that it makes right angles, and right angles are 90 degrees. So I'll show you in the picture. So here we have our tangent line, right outside the circle, hitting once. If we have a radius, there's our radius, we are going to get right angles where they meet. So where the yellow and the blue meet, we get a right angle here and a right angle here, remembering that those mean 90 degrees. So a tangent and a radius makes 90 degrees. All right. So with that theorem, we are going to apply that to different examples. So I'll move on down here. So, in the first one, I see a tangent with a radius. So now I know that right here is a 90-degree angle. They've already told us that angle Q is 25, and they want us to find angle O. Well, it looks like I have a triangle. Triangles always have 180 degrees for their interior angles. So let's start by adding the two that we already have. So far we already have 115 degrees in our triangle. So to find the missing one, we just have to subtract it from 180, because that's how many degrees are always in a triangle. And we get 65 degrees. Okay, so the tangent and the radius make a right angle, and we know there's 180 degrees in a triangle. All right, our next example, looking for my tangent with my radius. Here's my tangent. There's that line that hits once. There's my radius coming from the center. So there's my right angle. Now, this time we are not given angle measures. It's not like this one where all 3 interior angles add to 180. We're actually given side lengths. And when I have side lengths for a right triangle, I automatically go to the Pythagorean theorem. And if you remember the Pythagorean theorem, it's a squared plus b squared equals c squared. The most important one is the c, the hypotenuse, which is across from the right angle or the longest side. So here's my right angle. I look across. That means my c value is 61. A and B are my 2 legs. I don't know this leg. I'll just call it x. I do know that the other leg is 60, and this, it doesn't matter which one you call A and which one you call B. I'll just call that A and that B, but you could have switched them if you'd like. Plugging them in, x squared plus 60 squared equals 61 squared. Do the math out here. 60 squared is 3,600. 61 squared is 3,721. I have an equation to solve. Opposite of adding is to subtract. Always do it to both sides. Bring down the x squared I haven't used yet. Subtract these guys, we get 121. Last step, the opposite of squaring something is to take the square root. So those cancel out and we just have an x. And the square root of 121 is 11. So DE is 11. All right, let's look at the next one. Looking again for my tangent with my radius. There's my tangent outside that circle hitting once at B. Here's my radius coming from the center. I now know I have a right angle. I have a right triangle again. So let's see. I don't have angles, so I'm not worrying about that 180. I do have sides again. That's making me think Pythagorean theorem again. All right, let's look for the hypotenuse. It's the most important. So if I read across from that right angle, that's this entire side. And 6 plus 4 is 10. So that's my C. Now this is tricky because it looks like I don't have the other 2 legs. It doesn't, like I'm missing AB and I'm missing BC. Well, let's see. It wants us to find BC. So I'm going to put an X where they want me to find, which means there's probably a way for me to figure out AB. Well, there is. If you think about this, A is coming from the center of my circle. Look at AD. Isn't AD a radius from the center to the edge? Well, isn't AB also a radius? And in circles, all the radii are always the same measure. So if that's 6, so is that. Again, doesn't matter which one you call A and which one you call B. So I'll just kind of do this. So 6 squared plus x squared equals 10 squared. We'll do the math out. 6 squared is 36. 10 squared is 100. Got to move that 36 to the other side. We'll subtract it, do as opposite. 100 minus 36 is 64. And again, we will take the square root at the end. So BC is 8. All right, if you go to the next page here, there are 3 of those for you to try on your own. You can pause the video now and do them, or you can wait to do all of it at the end, up to you. They're just like the last 3. I'm gonna keep moving. Like I said, you can pause if you'd like. So on to our next theorem. Next theorem says, if 2 segments from the same external point are tangent to a circle, okay, same exterior point. So that's C, that's outside the circle. And I have two tangents coming down. Okay, so if I have two tangents coming from an exterior point, then those two pieces are the same size. That's what these little hash marks mean. So I'll just make an example here. If this is 7, then this must also be 7. That's it. That's the theorem. All right, we're going to practice that. So example 1, find EG. Well, I have a tangent here and a tangent here, both coming from E. They must be the same. Answer's 13. That easy. All right, example 2. I have a tangent coming from C, a tangent coming from D. They must be the same. This is a little bit trickier because they have x's in them, but if they must be the same, then they must be equal. So I'm going to set them equal to each other. So x plus 3, that tangent, must equal the other tangent. Solve my equation. I have like terms on opposite sides, so I'm going to move the smaller one. 2x minus x is 1x, or just x. That's it. Just wanted me to find x on that one. All right, this last one looks difficult. It's actually not bad at all. So you are looking for tangents from the same external point. I'll start with A. Here's external point A. There's its tangent. It matches up with the other one coming from A. So if that's 6, so is this. Let's find another pair of tangents. Now I'll come from B. B going to E is 4. The one it matches up with also comes from B, so BF is also 4. I have another pair of tangents coming from C. C to F is 7, which means C to D is also 7. That one's hard to see in yellow. I'll rewrite it here. So now you find the perimeter of the entire ABC. I'm just going to add all these numbers up. I have 2 6s, that gives me 12. I have 2 4s, that's 8. I have 2 7s, that's 14. 12 plus 8 is 20, plus 14 more is 34. It's a nice, easy theorem. There are 3 of those for you to try, just like the last section. So you can pause here and work on those. I'm going to keep moving. All right, the next page is kind of like a lot of vocabulary. So in a plane, 2 circles can intersect at 2 points, 1 point, or no points. So you can take a look at the first one. If I have 2 circles here, this guy intersected twice. That's one thing they could do. If they intersect at 1 point, so here's a circle, here's another circle inside of it, and it intersects right here once. Those are called internally tangent circles because the circles are lying inside each other. Internal, inside. Okay? And the word tangent, because it hits once, just like we've been talking about with tangents. Could also be externally tangent. So again, they only hit once. There's that tangent word. But they're outside of each other, so we say externally. So, and then the last thing they could do is they could intersect at no points at all. They could be completely away from each other like this. You could have a circle inside another circle. And there's a special case where they actually share the same center. This is called concentric circles. You can actually see the word center here, kind of. Okay, so those are a few things that can happen. So next section you'll do on your own. It's just a matching one, identifying internally tangent, externally tangent, or concentric. Just look at the pictures above. You can pause here and do that. I'm going to move on. Now, The next section is a little tricky because people get it confused with what we just did. What we just did is talking about the circles being internally or externally tangent. Now we're going to talk about internal and external tangent lines to circles. Okay? Common tangents are lines that intersect both circles in exactly one point. So, here's some examples of common internal tangents. So I have two circles here. I need to draw a tangent line that is in between the two circles. We're not saying that the circles are internal, we're drawing a line internal. So notice this line intersected this circle once and that circle once, okay? So that's an internal tangent because it's in between them. Another example of an internal tangent, two circles up against each other, still intersecting once, still in between the two circles. Okay. External tangents lie outside the circle. So this is a similar picture to this one, but you'll see that this time my tangent line is outside the circle rather than going in between them. Still hitting once on each circle, making it a tangent line. So again on this one's outside the circles, hitting once. Here's another one, outside the circles, hitting once on each circle. So either the tangent line's inside or outside. That's what that means. So one thing you'll have to be able to do is draw the common tangents. All right, I'm going to start by trying to draw the internal ones, a line that goes between them. There's one, hits each circle once. If there's one like that, I'll put arrows on these. There's usually another one that crisscrosses just like it. There it is. Hits each circle once. So it definitely has two internal tangents. Now we're going to draw ones that lie outside of them. Here's one. Try to draw a dash so you see the different types. Right, hits each circle once. And there's one on the other side. Hitting each circle once. So this has two external tangents. So it's two internal, two external, giving it a total of 4 common tangents. There's a lot in that picture. All right, I'll do one more of those with you. Let's start with internal. I need to try to figure out a line that goes in between them. This one's right here. All right, there's an internal. Hits once. So I see one internal. Just as a heads up, it doesn't have to have an internal tangent. It doesn't have to have an external tangent. It could have none of any of them. Externally, looking on the outside, trying to hit each circle once. There's one. And there's another one on the other side. So there's 2 external. Total of 3 common tangents. All right, 3 of those for you to try. Again, you can pause here and try those. And then the back is just, if you have extra time or want more practice, there is more of everything that we just did. It's nothing new, it's just mixed practice of the whole worksheet. And your teacher has the answer key for you to check your answers over when you're done. Or you can have someone email or call me if you have any questions. All right.